welcome to the last lecture of this series, and this is where the sweet part ends over there. Now, nonetheless, so we are working on this week on video analysis and video activity recognition, classification, and these kind of problems. So, while on one part you have learned about the theory of how to treat down these videos and as a tensor representation, and what is the implication of having these tensors in a newer format of representation. So, where what dimensions are going down in which particular level over there on your tensor. And then in the last lecture we have also done using a 3D CNN, which was you try to do a spatiotemporal convolution on top of videos and then come up with a classification system for your videos as well. Now, today we are going to come down to that other version of it, where you can use some sort of a recurrent neural network, or which is a time scale modeling neural network over there. And the particular one which we had studied in the lectures were called as LSTM, or long short term memory. So, today's particular exercise on the lab implementation is basically using an LSTM, but nonetheless you do recall that while we were studying LSTM, and in order to handle down videos, what we had was you would take in and decompose a video in terms of its frames. Now, you have a CNN from where you get down some sort of a latent representation in terms of features, and then these are not exactly your class labels over there for classification, but then these are features which would end up going down as time series stamped data onto your LSTM in order to come down with prediction per frame basis. Now, either you can predict all the frames in a series and what is the class label for them, or the other one is where you can predict only the terminal frame over there based on all the previous frames which have come. So, we are going to stick down to the latter, where you are going to just classify the terminal frame based on whatever has happened on all the frames before it, and that is the kind of a classification which we are going to do. So, we are going to use the same data set which is this UCF 101 data set, where you have 101 different classes of activities which have to be recognized by this kind of a learning engine. Now, as in the earlier case, we had not used all the 101, but just 5 of them. So, here also we are just going to stick down with 5 of them, and in fact, the data preparation and everything is going to stick down to the same way. So, let us get in over here. So, what we have is we have broken down these lectures into 3 different notebooks to make it easier for you to understand and keep on running. The first one is where we do the pre-processing of training a CNN in order to extract out these features over there. Now, if you look through it, the first and foremost thing is that you need to have this lecture 59's pre-processing part already executed, because you would need to have access to these frames extracted from the video and kept down in one particular ordering. Now, if that is not present, then this part does not work. So, that is one part of the exercise which from the last lecture, which you need to essentially implement and keep it ready on your side. The next part is that you have 3 different parts over there, which is 60A, 60B and 60C. So, I am starting with 60A now, and then eventually I would be going down to 60B and 60C. So, in 60A we are just going to learn down on how to train the first level CNN and not the LSTM yet coming into picture. Okay. Now, as in with any kind of a CNN which we had, so we are just going to stick down to the first part of the header, and that is a pretty standard header which we have been using for all of them. Now, from there is to check down if GPU is available or if it is not available, and so what we do addition to that one is that we stick down this extra configuration which is called as pin memory, and pin memory is basically something which is hardware dependent. So, what it essentially does is that your CPU has multiple number of buses over there which connect down to your hardware resources, including your RAM, including the PCI bus, and then the DMA allocation over there. So, if pin memory is set down as true, so what it allows is that across different batches which are getting loaded down over there, because you have some sort of a parallel data loader coming into play. Now, once this data loader comes into play, if the memory channel is defined over there, then the arbitrator does not come into play over there, and this will speed up the whole process. So, this is what we need to define over here. Now, in case that you do not have a GPU, then you can pretty much set it to false, and that is something which is recommended. The only concern about putting the pin memory true for using within a GPU was so that, because it is a shared bus between your CPU to your RAM and your PCI bus via which your GPU is connected, and if you are setting this true, then this arbitration does not have a lot of overhead time requirement coming down over there. So, this is the only reason over there. You can implement the same thing with all your earlier exercises as well, but you will not be seeing too much of a change in terms of execution time. Here the whole change comes in because the amount of data which you are handling, which needs to be loaded down from the hard drive side over there, is seriously massive, and for that reason this really makes a significant impact on what would happen with using it or without using it. So, the next part is we basically have two different folders over there, which is created down from the lecture 59 pre-processing part of the code, and that is one of them is called as the train_5 class, which is the training folder, and the other one is your testing data folder over there. Now, what we need to do is that we take in all of these videos and we resize them to 256 cross 256 size, and then we do a center crop of 224 cross 224. Now, one of the reasons for doing this center crop of 224 cross 224 is that obviously your rest of the network over there, most of these being ImageNet kind of a network, they would be needing a data of 224 cross 224. The other part of it is that significant amount of pixels on the boundary over here for this particular frames, they are not in any way informative, and that is the reason why we decide to crop from the middle part over there. Now, this is very much typical to what you are trying to do and what is your philosophy over there. Now, we have just found out this kind of a technique to be much better suited for most of these problems over there, and sometimes if you feel that your peripheral parts of the image also have some information which is significant towards video analytics and does capture some of the motion information, then please do not discard by cropping it out, please retain those parts of the information as well. Okay. The next part is to load down all of these data. Now, what you have essentially within these two folders is basically a few more folders which have image frames extracted from the video, and so here the whole job is basically from your image folder you would be initializing your data loader. So, your train data set is something which resides inside your image folder. So, this is what we have done in the earlier cases where your whole data was located within a folder. So, what you could do is you have to point down a pointer which goes into the directory structure over there, and that acts as initialization pointer for your data loader, and then your train data loader or as well as your test data loader, any of them can initiate their workers to keep on loading it out. Now, you need to specify your batch size, and we are choosing down a 128 batch size over here, and the number of data loading workers as 4. Now, this number of workers is pretty much dependent on your hardware configuration, which is the total number of memory channels which are available to your system. So, if that is 4, then you setting it down to 4 is good. If you are setting it down to any value lesser than that, it works out good, but then you are under killing, you are basically killing down the advantages which you would have otherwise got. And now, if you are setting it to a value greater than 4, then what would happen is that most of the time you will not be able to have the best optimization of resources, because these extra workers will still be parked, they are not going to do it because you do not have a physical channel available anywhere. Now, another part is that we decide on shuffling over here, and this is to get into your option of a stochasticity coming into play, which meant that basically if we have a stochastic gradient descent or an ADAM kind of an optimizer coming over there, then across different epochs when it starts invoking this data loader over there, then the same batch at different epochs should not be having the same amount of data or the same should not be having the same samples over there basically. So, they need to be some sort of a shuffled out. So, this shuffling set down to true is something which is helping me do that, but in case of my test data I am not going to use that shuffle because it is just a feed forward and a validation stage. So, in fact, this shuffle has some extra time incurred on top of it. So, we do not make use of that. Okay. Next, so we just get down what is our total number of train and test samples, and this was pretty straightforward. Now, getting into our network, what we are trying to do is use a ResNet 18, and we use a pre-trained network which was trained on the ImageNet data set itself. So, that there are two advantages. One is because it is a pre-trained network, so it is easier to converge over there, and then definitely the major advantage which you get down is that since it converges, that is no way a great advantage over there, but then your total number of epochs which you would have otherwise taken to train this whole network, that is also going to be less. So, it is a very faster way of getting down. So, this is one stage of domain adaptation which we also apply to our video analytics problem. So, this is just a printed version of it, and since we have done a lot of them, I am not going through these any further. Now, the next point is getting into your parameters and printing it out. Now, this is also straightforward from your earlier exercises, and there is nothing major which comes in, except for the fact that now we will have to modify this network to be suitable for the kind of a model which we are using. Now, our job is to classify it into 5 different classes. So, I am just going to replace this last layer over there. So, my last layer was basically on my RESTnet was something which was connecting 512 neurons onto 1000 classes or 1000 neurons over there for classification. Now, here I do not have 1000 classes, but I just have 5 classes. So, I decide to replace this last layer over there with a linear connection of 512 neurons to 5 neurons, straightforward. Now, if a GPU is available, just typecast and convert it onto GPU, so that you can set everything running on the GPU side over there. Now, on my criterion, the cost function for training is negative log likelihood loss, and it is because it is a classification problem, and we have been sticking down to the same loss function for majority of them, and for optimizer we stick down to taking Adam for faster and better convergence coming into it. Next comes into our training part over there. Now, for the training, it is again straightforward that we just initialize these losses which we need to take down over there, and then start our data loader working down over there. Now, within the data loader, what I am going to essentially do is look whether my GPU is available, then typecast my inputs and which are input images and the labels over there onto a GPU variable, and then do a feed forward over the network and get my output, and then I have my prediction of the predicted classes over there. Now, these predicted classes can be used for finding out how many of them are correct and how many of them are wrong. Now, once this part is done, so I can actually set my optimizer coming into play. So, for that, the first part is to zero down all my gradients which we have done, and then you find out what is your total loss. So, this loss is based on the criterion evaluation of negative log likelihood. Then you do a nabla of your loss with this backward, and then you have your optimizer dot step for the update part of the function to run down, and then you have this whole thing running, and finally you get your accuracy at the end of one epoch during train. Now, once that is done and your network is updated, what we do is we put down our validation set into play, or this is the test data which was there over there. So, you do the same thing, you do a forward over there, and then find out what is your loss using your criterion, as well as you find out what is your so basically what is the total number of correct predictions in order to get your accuracy, and then you have those also computed and loaded down into your blank tensor, and then comes your standard plotting part of it, and finally your timing part of it. Now, if we keep on running this one for 10 epochs as we have done over here, so it does not take much of a time basically. So, per epoch it is going to still take down about 5 minutes 42 seconds, and in total over all the 10 epochs it takes me about 97 minutes. So, that is barely about 1.5 hours of what it would be taking. Now, keep in mind one part that these are very dense data, a lot of images over there on which you are training. So, the time is not something weird of 1.5 hours. So, these are by now you know that on practical data sets on bigger ones, one of the major challenges which you would be facing down with any kind of a deep neural network is that it is going to take a significant amount of time. So, if you look into our losses, you would see that your test loss or the validation loss is still above the training loss. So, that is a good symbol that it's you have a good amount of generalizability, but you are still not exactly overfitting over there, because you do not have an influx point coming up over there. Now, if you look into your accuracy over there for a frame level prediction is somewhere around 80% over there. Now, that is something to be very happy around, and in fact, your train accuracy is something which is going down close to 100%. Like, stay very happy over here, because this happiness is something which is quite important. Now, the next part is and then this also gives you another important part, that just a frame level one is 80% accurate. That is great. Now, on the next part what we do is we need to use these this network and the weights which are trained over here for another purpose as well, and that is when we try to find out the features for an LSTM. So, for that what we are trying to do is we just save down just the weights in terms of dictionary state. You do not need to save your derivatives or gradients or anything over there. It is just the pure weights over there which need to be saved. Okay. Now, at this point I would move down to the next series of the 1 which is 60B, and here what we do is essentially use this earlier pre-trained CNN in order to extract out features which represent one individual frame over there. So, the first part is your customary loading of your header files over there and all the header libraries, then to check down for your GPU, and then finally what you do is, so here what we have is that in the, if you remember from your lecture 59, then there are two different pickle files which we had stored down, and this had the list of all the videos and the frames, frame names which were present in your training data set or was present in your testing data set. And this is important because now what we are going to essentially do is, for every single image over here, we get down a tensor representation. It is no more an image file, but a single tensor corresponding to that particular image over there. So, we start by loading these ones and then look into what is the classes present over there. So, these were the 5 classes which across which we were classifying in the earlier case. So, where you got down somewhere about 88% accuracy. Now, the next part is to create your network over here. So, what we are essentially going to do is you load down, so we are still going to use the ResNet 18 over there. Okay. Now, on the ResNet 18, what we are going to do is you need to load your dictionary states over there. And so, what these dictionary states are essentially is all the weights which were there from the previously stored one. So, this was the file name which we had used for storing down all our weights in the earlier case, and I am just going to reload it over here. Now, once I have that one, what I next do is, on my model over here, I will be deleting this last layer. So, my last layer is basically this 512 to 5 neurons over there, and I am just going to delete that part over there. So, this thing gets deleted. Now, once that is deleted, so I am just left with, given an input image over there, I am going to get a 512 cross 1 tensor straightforward. So, every image in terms of just a simple tensor of 512 elements present over there. Next, if we have a GPU, we just convert this model to CUDA, so that it is available over there, and now comes our next part of it, which is for feature extraction or representing each frame in terms of just this simple 1D tensor. So, the data transform is still going to remain the same, that you resize it to 256 and then crop the center part for 224 cross 224 sized image over there. And then what we do is, here is where you are going to convert down each and every frame onto a tensor. Now, it is independent of whether it is present on my training data set or on my testing data set. I am going to have it for all of them, because that is the input which goes down onto my LSTM over there. So, what we essentially do is we find out all the frames present within this frames folder over there, and then for each of them this image is opened up, and then you have the transformation applied over there. Now, what you would be doing is you do a forward pass over my model or the straight pass over this network over there. Now, keeping one thing in mind, that whatever comes out on the output over there again needs to be recasted into one single tensor over there, and then this is this view operation which sets up my last part of the tensor coming out of it. Now, once we have all of these available, then I need to save it out, and so this is part where I save my tensor in terms of a .pt file. So, each image now stored in terms of a tensor, in terms of a PyTorch tensor over there. Now, once this is done for my training one, I will be doing the same thing for my test list as well. So, this is where I load it down from my test list, which I had loaded on my pickle files over here. So, this was my test list which is over here. Now, based on that, I am going to again run down everything and then also store them out, and now this gets stored in terms of a different directory called as test. So, I have each frame extracted and represented in terms of its 512 cross 1 1D tensor. Okay. Now, this is the second part which gets over, and then we get into the last and final part, which is where you are going to train your LSTM. Okay. Now, within this part, what comes down is we would be for the first part is just your header over there. So, that is straightforward, we are not going to make any change over there. Now, and you again check out for your GPU, because you are switching away from one Python notebook onto the other Python notebook session, you need to re-invoke and check out all the variables once again as well. And then you again load down your train path and test path. This is to get down what are your which all images are there in your training data set and which all images are part of your testing data set over there. And then you basically create out a list for each of them in order to facilitate your loader. Now, one important part which we do over here is that we need, because we are not making use of the data loader any further. Data loader is something which can work only on images. So, here I have .pt files or PyTorch files with all of these tensors present. So, I don't have an option of making use of data loader. So, what I am essentially trying to do is that within each run over there I am trying to shuffle off these indices. So, in order to shuffle these lists over there, what I will have to do is I have a frame, a list of all the frames for one particular example, and corresponding to that I have a class label given down over there. I need to have this pair and shuffle up this pair, and for that reason the simple way of doing it is just zip these pair into a zip file, then you can shuffle up this list over here and then again unzip this folder in order to create get these shuffled up lists over there. Okay. So, now once that part is done, then we are going to load down all of these features over there. Now, once it is done, we start defining our LSTM. Now, the LSTM which we have defined over here is using the module called as nn.lstm, and within that what goes in is basically your input size. Input size is something which is mapped from the input tensor size. So, for each time frame over there I have a 512 cross 1 tensor. Okay. So, if I have say 20 timestamps over there, it becomes 20 cross 512 for me. So, this input size is what goes down over there. Next, you give down what is the size of the hidden layer, and for our purpose over here you basically have all the hidden layers with the same number of neurons given down. We do not make any change within this. Now, you can also give this hidden size as a tensor, separate tensor, where you can specify what is the total number of neurons across each of them. Now, remember one thing, that there are no convolutional connections or anything, they are all fully connected layers. So, you do not need to put any further parameters, you can just specify what is the total number of neurons per hidden layer. Then what is the total number of layers over here, and finally this rest of the part argument over there, which is batch first is equal to true, is to set this ketone over here, because if you remember on our video tensors what we were doing is you had the batch number, then you had channel number, then you had your time over there, then you had your x and then your y. So, this is how it was going down. Now, here since we have transformed each frame over there onto a tensor, where what you have is you have your batch number, then you have your timestamp, and then you have your tensor representation. So, if I have say 20 frames over there and a batch size of 100, then I have 100 cross 20 cross 512, because each frame is now represented in terms of a 512 cross 1 tensor over there. So, that goes over there, and your final part is just a classification over there which connects down hidden neurons, the total number of hidden neurons onto a class. So, that is because each hidden layer has the same number of hidden neurons. So, we are not making any change over there. If you had passed down basically a tensor over here defining each different layer in a different way, then you have to have this hidden size as the last hidden layers number of neurons over there, and that maps down to my total number of classes, which for me is 5. Okay. Then my forward pass for the LSTM is pretty simple, that whatever is my input, that is what maps down to my output. Now, remember a thing, that this LSTM module inside has all of the rest of the operations for forget gate, retain gates implemented over there, and then how it does time unwrapping and training within it. So, we do not need to specify each of them, we just need to specify the atomic structure for an LSTM block over here. Now, once you have your output, then what you can do is that we just need to take down the state of the last timestamp, because essentially if I have 20 frames over there, then I am going to get down a prediction for each of these frames coming out, but I need to get it only for the 20th frame and not for 19th, 18th, 16th, 17th up to my first frame. That's not necessary for my work over there. I just want the terminal frames classification coming out. So, that is what we are essentially doing over here, that your output for a bunch over here, which is for a tensor, a timestamp tensor, is what is going to give me just one single classification output for this whole time frame volume. Now, then we start our training routine over here. So, within your training routine, what you do is one is just check down for your available GPU or not, and then typecast your inputs and labels over there. Now, remember your inputs are basically your inputs of that tensor over there and fetched out in terms of a batch, and label is for each single video block within that batch. What is the label for it? Okay. Next, I do a feed forward, get my output over there and find out what is my prediction coming out of it. Now, once that is done, next is zero down your gradient so that we can start our optimizer, find out your loss using your criterion function. Now, here also it is a classification problem which we are solving. So, we are going to stick down to the same criteria of a negative log likelihood coming into over here, and then we do a derivative of the criterion function on nabla of the cost function. Then you have your optimizer dot step or the update routine written down over there. Then you are just going to find out whether how many are correctly classified and what is the accuracy which comes over there. Now, this is what goes down within your training part over there, and then you have your test routine written down in order to do the testing part over there. So, typically in the earlier case we were writing this together, but here we are just splitting it out. Okay. Next, you can initialize your network. So, what we do over here is my input feature dimension is 512. So, that is my input size which goes over here. I have every hidden layer which has just 8 neurons over there. I have 2 such hidden layers over there, and my total number of outputs is 5. So, this is what I do in order to initialize my LSTM, and which is from my module which was defined in the earlier case. Okay. Then I have my optimizer and the criterion, both of them defined over there, and then I start with my epochs. Okay. Now, I have my I am going to train this one for 1000 epochs, and I have a batch size of 32 which I am going to take down over there. Now, while I am taking a batch size of 32, I am also taking a time length of 32, which means that 32 frames taken down together, and it is going to give me one single output for classification. So, following that, what we do over here is one thing which we need to look is that my total number of frames which are present over there may not necessarily be an integral multiple of 32. So, there will be some frames which are left out if I am trying to do a batch fetch. So, what this part does is that we find out what is the constitution of the last batch over there, and if needed then so that's just a modulo operation which you need to do to find out what is the constituent of the last batch. Now, once you get down this last batch constitution, so that may be something lesser than 32 on the batch size over there. So, that also needs to be processed, otherwise you are not using all of the data, you are just skimming out some of this data over there. So, this last batch part for the train and test, both of them are written down so that you have access to this remaining residual data as well. Okay. Now, we start across all of our epochs and then set down our losses to 0, and then it starts up. Okay. Now, once it starts, you have your data loader coming into play, and this was because we had modified and stored it down in terms of our pickle files which could now be loaded down. Sorry, not pickle files, but PyTorch files which could now be loaded. So, they were just PyTorch tensors over there. Now, what I do from there is once I load it down, I need to convert and get back my labels and my tensors appropriately represented. So, that is what is set down over here. Now, next part is to get into my training routine over there and find out what is my losses coming down. So, this train routine is something which we have written down in the earlier case over here. Okay. So, this is my train routine written down for my network when I am training it out, and this is my test routine which has been written. Now, in the earlier exercises on CNNs and stuff, what you were looking down is that we used to fuse everything together and write, but this is also an option because I can now allow myself to do just a pure simple function call over there. Now, once you have that thing written down, you get down your training losses coming down over there, then you have your train accuracies calculated as well. Now, once that update and everything happens down during your training, then you have your test and validation part being taken care of over here. And then this is for your last batch which you need to take care of. So, once that's once you have everything running over all the regular number of batches, so the last residual number of things is what gets taken care of in the last batch present over here. Now, having done that, now you can get per epoch wise what is your average accuracy and coming out of it, and then you can decide on plotting it out. So, this is straightforward what we do over here, and then we set this one running. If you see this one running, this It initially starts over here with a training loss of about 0.05 and an accuracy of 18% and a test accuracy of about 16% and takes about 11 seconds to finish off. So, one thing for sure is that while your CNNs were taking much larger to finish off because it was a residual network and a dense connection over there. Here you just have simple tensors which come down, you do not have the whole image going into it, and fully connected neural network for your LSTM modules over there. So, the number of parameters is much lesser. So, it takes much faster to converge onto them, but nonetheless the starting accuracy is at a much smaller zone over there. And if you look over here, so it shows down at 0 seconds. So, technically it is not like 0, but it is a much lesser value. In fact, they finish off in a few milliseconds, and you see this accuracy starting down at about 11% and then it keeps on going down. Now, if we go till the end of this routine, then we would be, just let me, yeah. Okay, so let's come down. Yeah, it's about 800, 900, and then we are close to 1000 epochs over here. Okay. So, the total time it took for me to converge over 1000 epochs is just merely 8 minutes over there. Now, let us look into the accuracy graphs over there. It starts with about 25% of an accuracy, and then here by the end of 1000 epochs, my test accuracy is somewhere barely about 45%, my train accuracy is about 50%. Now, that is not an impressive figure given the fact that my CNN already had an 88% of test case accuracy over there, but nonetheless you need to keep another thing in mind, that this whole network over here has not yet actually converged in any way. It still shows a increasing trend in terms of its accuracy as well as a falling trend in terms of its loss, which is coming down over here, and that keeps in mind one thing, that we need to train it for more and more number of epochs as well. So, you can keep on doing this for beyond 1000 epochs, and typically I would be suggesting about going down to close to 10,000 or even more number of epochs in order to see your saturation coming down. So, that is where we come to an end for understanding LSTMs for video analysis and end of this lecture series as such. So, for those of you who are taking down the test for the final examination as well, so we wish you all the best for your exams and all endeavors in future and life. With then, thanks, and we wish you goodbye from this course.